Earth's rotation is slowing down and could explain why we have oxygen. Ever since its formation about 4.5 billion years ago, Earth's rotation has been gradually slowing down, and its days have gotten progressively longer as a result. While Earth's slowdown is not noticeable on human timescales, it's enough to work significant changes over eons. One of those changes is perhaps the most significant of all, at least to us. Lengthening days are linked to the oxygenation of the Earth's atmosphere, according to a study from 2021. Specifically, the blue-green algae, or cyanobacteria, that emerged and proliferated about 2.4 billion years ago, would have been able to produce more oxygen as a metabolic byproduct because Earth's days grew longer. The enduring question in Earth sciences has been, how did Earth's atmosphere get its oxygen, and what factors controlled when this oxygenation took place? Microbiologist Gregory Dick of the University of Michigan explained in 2021. Our research suggests that the rate at which Earth is spinning, in other words, its day length, may have had an important effect on the pattern and timing of Earth's oxygenation. And there are two major components of the story. At first glance, don't seem to have a lot to do with each other. The first is that Earth's spin is slowing down. The reason Earth's spin is slowing down is because the moon exerts a gravitational pull on the planet, which causes a rotational deceleration, since the moon is gradually pulling away from Earth. We know, based on the fossil records, that days were just 18 hours long 1.4 billion years ago, instead of today's 24, and half an hour shorter than they are today 70 million years ago. Evidence suggests that we're gaining 1.8 milliseconds every century. The second component is something called the Great Oxidation Event, when cyanobacteria emerged in such great quantities that Earth's atmosphere experienced a sharp, significant rise in oxygen. Without this oxidation, scientists think life as we know it could not have emerged. So, although cyanobacteria may cop a bit of side-eye today, the fact is we probably would not be here without them. And there's still a lot we don't know about this event, including such burning questions as why it happened when it did, and sometime earlier in Earth's history, and not earlier. It took scientists working with cyanobacteria microbes to connect the dots. In the Middle Island sinkhole in Lake Huron, microbial mats can be found there that are thought to be an analog of the cyanobacteria responsible for the Great Oxidation Event. Purple cyanobacteria that produce oxygen via photosynthesis and white microbes that metabolize sulfur compete in a microbial mat on the lake bed. And at night, the white microbes rise to the top of the microbial mat and do their sulfur munching thing. When day breaks and the sun rises high enough in the sky, the white microbes retreat and the purple cyanobacteria rises to the top. And now they can start to photosynthesize and produce oxygen, said geomicrobiologist Judith Klatt of Max Planck Institute for Marine Microbiology in Germany. However, it takes a few hours before they really get going. There is a long lag in the morning. The cyanobacteria are rather late risers than morning persons, it seems. And this means that the window of daytime in which the cyanobacteria can pump out oxygen is very limited, and it was this fact that caught the attention of oceanographer Brian Arbick of the University of Michigan. He wondered if changing day length over Earth's history had had an impact on photosynthesis. It's possible that a similar type of competition between microbes contributed to the delay in oxygen production on the early Earth, Klatt explained. To demonstrate this hypothesis, the team performed experiments and measurements on the microbes, both in their natural environment and a laboratory setting. They also performed detailed modeling studies that, based on their result, to link sunlight to microbial oxygen production and microbial oxygen production to Earth's history. Intuition suggests that a 12-hour days should be similar to one 24-hour day, two 12-hour days to one 24-hour day. The sunlight rises and falls twice as fast, and the oxygen production follows in lockstep, explained marine scientist Arjun Chenu of the Leibniz Center for Tropical Marine Research in Germany. But the release of oxygen from bacterial mats does not, because it's limited by the speed of molecular diffusion. This subtle uncoupling of oxygen's release from sunlight is at the heart of the mechanism. And these results were incorporated into global models of oxygen levels, and the team found that the lengthening days were linked to the increase in Earth's oxygen, not just a great oxidation event, but another second atmospheric oxygenation called the Neoproterozoic oxygenation event around 550 to 800 million years ago. We tied together laws of physics operating at vastly different scales, from molecular diffusion to planetary mechanisms. We show that there is a fundamental link between day length and how much oxygen we can be released by ground-dwelling microbes, Chenu said. It's pretty exciting, and this way we think the dance of the molecules in the microbial mat to the dance of our planet and the moon, we link them, and the research was published in Nature Geoscience. This is on Science Alert by Michelle Starr. Please leave your comments, and thank you for your support. Please support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.